Today, I'm going to talk a little bit about Moonbeam X and XCM. I'm going to start with our experience and what's to come. And that what's to come, it's basically a spoiler alert as remote EVM calls through XCM. But before I start, I want to sort of give a little bit of yesterday when I was hearing some of the talks, a lot of them were focused on interoperability, right? And because we think that the future is going to be multi-chain. And so the multi-chain future will need this GMP protocols to be able to communicate all these different chains that are going to exist out there. But one important GMP protocol or general message passing protocol, it's going to be XCM, because that is the main way that blockchains inside the Polkadot ecosystem will communicate with each other. And XCM, it's actually can be expanded outside of Polkadot, but it will be mainly used in Polkadot. And so, yeah, let's start with the presentation. It's going to be a mix between, high-level general examples, but we'll dive down into the tech as well. So first, let's do a brief overview of what XCM is. And we're going to start with a very high-level overview, and then we're going to, dive into some more of the technical concepts, like I said before. So, XCM is the native intra-communication layer for Polkadot. It's what allows all the participants in the Polkadot ecosystem to communicate with each other in a native fashion. And XCM by itself, it means cross-consensus messaging. And it's a very generic message format with a given format that has a set of instructions. And these instructions, the way that I like to, give an analogy on this is that imagine, I am the virtual machine or the XCVM that executes these instructions. And I'm told, stand up out of the chair, walk 10 steps towards your right and flick the switch. And then an action, it's going to result out of these instructions, right? In this case, the light will be turned on. But, in the case of XCM, you will have asset transfers, remote calls, and so on. And so these two elements, the XCM and the XCM VM, it's XCVM, it's what basically allows these sort of message to sort of, be executed on different chains. On the right-hand side, I do have sort of like three actors in the Polkadot ecosystem. Polkadot itself as a relay chain, we have Moonbeam, and then we have other parachains, just to name a few. We have Akala, Bifrost, Parallel, Interlay, Centrifuge, whatever. And so the communication channels between these participants is what allow these messages to basically move around the ecosystem. And one particular thing about this communication channels within Polkadot is that they're unidirectional, meaning that if Moonbeam wants to connect with Akala, we got to open a channel on that direction. And if they want to communicate back, there has to be another channel coming back. Channels between parachains and the relay chain are native, are basically they're given to you once the parachain connects to the relay chain, so you don't need to do any particular action. And these channels, they have names. It's easier to refer to them with little names. And so basically we refer to UMP when there's a message going from Moonbeam to the relay chain because it's upward message passing. DMP, it's downward message passing, that it's a message from Polkadot to Moonbeam. And then we have horizontally relayed message passing, which is HRMP, which will evolve into XCMP. And this is the sort of the message that are passed between parachains, Moonbeam and other parachains, or between other parachains. And so it's common to refer to, I sent UMP to Polkadot, meaning that, it was from Moonbeam to Polkadot and so on. If you want to learn a little bit more about XCM, I highly recommend you check this GitHub. I'm always going to leave URLs in the slides, either with stuff from our documentation or GitHub URLs or anything, in case you want to learn a little bit more, because we do have limited time. And so if I would have talked about everything about XCM, it would have been like a week. And so let's do first a very simple example. Let's do remote transfers. How do we move, for example, Polkadots or dots from Polkadot to Moonbeam? And so once again, let's start high level. Let's say Alice on Polkadot, she wants to send some dots to another account called Aleth on Moonbeam, right? So Alice and Aleth, they might have different owners, different private key owners, or they might be the same. That doesn't necessarily matter. But the important thing is that there are two separate set of actions that are going to take place. One is going to be some XCM instructions that are going to be executed on Polkadot, and the other is going to be some XCM instructions that are going to be executed on Moonbeam. And so what's going to happen at the end of these executions of XCM instructions is that Alice is going to, through the execution of the XCM, transfer some dots to something called a sovereign account, okay? And I'll explain what a sovereign account is on the next slide. But the important thing here is that the transfer has to be through the execution of XCM. If Alice would have just transferred some balance to the Moonbeam sovereign account, it would just be a beautiful donation, basically. I mean, it wouldn't actually account for the token transfers to Moonbeam, okay? So basically, once that XCM part is executed, an XCM message, it's sent to Moonbeam, all right? And in this case, those XCM instructions, when they're executed, they're gonna mint XC dots, which are, in our case, a one-to-one representation of the dots that were sent by Alice. And they're going to be transferred to Alice, or whatever address Alice actually decided to transfer them to. So this is very high level, right? But before we take a deep dive into the tech part, let's talk about the sovereign account. And the sovereign account is basically an account that it's owned by the chain itself. All right, it's a keyless account, so nobody knows a private key. And the chain itself as a whole, as an entity, owns the account, basically, okay? And so each chain, so Moonbeam has a sovereign account on other parachains, which actually has the same address, and it has a sovereign account on the relay chain, right? So you can actually find the account of Moonbeam on Akala, on Fala, on Parallel, etc. And also the relay chain has sovereign accounts on the parachains as well. The analogy that I like to give about sovereign accounts is that if you think about, in general, how sort of Ethereum bridges work for transferring tokens, it would be, and I'm quoting myself because it's not like that, but it's a good analogy, the smart contract where you lock the tokens. The main difference here is that it's not a contract logic, but it's an account secured by the protocol itself, which is a lot more secure. And the addresses of these sovereign accounts are deterministic, for sure. And in the case of parachains, they're defined by the parachain ID. So in the case of Moonbeam 2004, so there's some equation, so some function on the right hand side that I pasted, and you can find the actual code in the links that I've shared on the top right corner. But you basically can calculate it using the parachain ID. And in the case of the relay chain, it's similar. You basically encode a word and then just trailing zeros. And back in the day when I started interacting with XCM, I would run this code very, very often. But now you can actually visit Sean Trabisi's Substrate.js utilities, and he added a function to calculate the sovereign account of whatever parachain ID you want. So now understanding what the sovereign account is, let's go back and think about our example of remote token transfers, right? Alice will transfer some tokens to the sovereign account of Moonbeam, and then Alice will receive these tokens. So the part that gets executed on Polkadot, it's only one XCM instruction, and it's basically transfer reserve assets, and you can find the execution, what it does on this URL. But like I said, basically takes funds from Alice and deposits them to the Moonbeam sovereign account. And basically also sends an XCM message to Moonbeam, appending prepending two XCM instructions for security, okay? And so basically the palette or the plugin that implements XCM token transfers need to provide the other two XCM instructions to ensure that that actually works. So if we look into the code of how this instruction works, this looks really nice, but I want you to focus on the following lines, okay? You can see here that even though I'm not a Rust developer, I barely know how to read Rust, but luckily enough, I know enough to read this part. But you can see that this part right here, basically just transferring the asset from an origin to a destination, right? So in this case would be dot from Alice to the Moonbeam sovereign account. And then down here, you have the part where the following or the next XCM message is built, where you actually prepend these two instructions, and then you insert whatever other instructions were given as an input of the instruction itself. And then this XCM message gets sent to that destination, which in this case is Moonbeam. So what happens in Moonbeam now is that you have 4 XCM instructions, and the execution of these 4 XCM instructions will result in Alice having just tokens. Okay, so in this case, XC dots. The first one is reserve asset deposited, which mints the representation, but it doesn't send it to Alice just yet, right? It keeps it in a state called holding, that it's basically just like no one owns it, but it's there to be used for something else. The next instruction is clear origin, and this removes the origin information, meaning that before the origin was actually the Polkadot relay chain. And so now we don't want any action to be basically done in behalf of this origin. And so we remove the information of the origin. And the next instruction, it's very common to see this instruction in many XCM messages, because this instruction is what allows you to execute something on Moonbeam itself, right? So this buys execution time or block space, and then to do something, right? And in this case, we're actually executing 4 XCM instructions with that execution time. And the way that we charge for this execution time is we take assets from holding. So in this case, the mint assets. So if Alice sent 1 dot, we'll take out of that one XC dot, we will take some asset to pay for that execution. And the last instruction is the one that actually transfer the assets to Alice, right? In this case, it will not be 1 dot, it will be a little bit less, but it will transfer the asset to Alice. And this is a summary of what a remote token transfer is from Polkadot to Moonbeam. Note that depending on what type of transfer we're doing, the instructions might vary a little bit, especially these two. The one that gets executed on Polkadot, and the first one that it's on Moonbeam. It just depends on if we're transferring back dots, or if we're moving Glimmer from Moonbeam or to Moonbeam, etc. So let's review now a little bit of the Transact through XCM. And this is very important because at the end of the presentation, we're going to talk about remote EVM calls, and the Transact through XCM is key for this. So remote Transact through XCM allows you to basically natively execute an arbitrary data on another chain, right? So 2 chains can actually execute some specific code on the other chain, allowing them to basically do whatever they want, if you think about it, right? So, and I'm going to give a practical example of how this is being used. One important thing is that the execution normally is done or is dispatched from a keyless account. So in the case of Moonbeam, we provide a mechanism so that you can control an account on Moonbeam through XCM. And this is a keyless account, right? You don't know the private keys, but you actually control it using an account on another parachain, which you hold the keys to, right? So it's sort of you don't own the private keys, but you own the account, because the only way that you can access that account is through XCM from your chain and using your private keys. And so let's do it as we did before with the transfer example. Let's do an example of remote Transact. And as always, I invite you to check the code that I always put in the top right-hand corner of the slide. So let's say we're transacting from another chain into Moonbeam. And so on the other chain, you could have an XCM instruction that includes some instructions to set an asset to pay for the remote execution. This is similar to what we did before. It is not really mandatory. It just really depends on how this is constructed. Because, for example, in the case of dot, remember that instruction included 2 instructions. And in this case, we cannot allow that to happen. But certain specific scenarios could actually allow this sort of construct to happen. And then on Moonbeam, depending once again on what happens on the origin chain, you could have different instructions, right? The core 3 are withdraw asset, buy execution, and transact. But you can also add the send origin, which is a way to sort of mutate who is gonna dispatch that from which account you're gonna dispatch a transaction from. And so the send origin basically transformed the origin with a given interior. I can tell Moonbeam, hey, I want to dispatch it from this account that I own on Akala, for example, right? And then Moonbeam will create a derivative keyless account out of this information. The next instruction is withdraw asset, and this removes assets from an account and put them in holding. Remember that holding is the state that you can use the tokens for something else. And then we're going to use those tokens to buy execution time. And then we're going to call the Transact instruction, which just dispatches arbitrary call data that you provide in the origin chain. And then you have all the URLs in case you want to see how this gets executed. And so to give a more practical example, let me show you how Lido does liquid staking. And Konstantin did a way better job that yesterday that I'm going to do here today. This is a very simplified mechanism that it takes for granted a bunch of things that are happening, but this just to show you the core basic things that are happening, right? And so the idea is that a user signs a transaction on Moonbeam to initiate this like remote transact on Polkadot. And so that transaction will interact with some Lido contracts, and Lido will give you the liquid derivative token, ST dot in this case. And after, I don't even know the right order of things, but at some point, the contracts are going to interact with a precompile, an XCM precompile, that is going to send an XCM message to Polkadot, basically doing a remote transact, a transact instruction with some other instructions attached to it or before it. And what this remote transact is going to say is, hey, Polkadot, how you doing? So I want you, right, to stake XYZ dots to this given validators, right? And like I said, this is a little bit simplified because you have to think about, that you need to pull some dots together and so on. But if we abstract all the complexities and all the logic behind it, like I said, Lido did an amazing talk yesterday explaining all this. It's great to at least understand that what's happening is that a user can stake on Polkadot, but the actual initiation of that call started on Moonbeam, right? So you're communicating to chains natively and in a very secure way. All right, let's shift gears and change to another important topic in XCM. And it's going to feel like I'm like moving around, but this is all related, and we're going to get to it at the end with remote EVM calls and multi-locations. So multi-locations is a way to represent locations in the ecosystem. And I think one of the developers at Moonbeam, Gorka, explained this to me using folder path, and I really like this idea. And so I'm going to use it to explain to everyone watching and who's watching the replay as well. So imagine you can think of a multi-locations like folder path, right? Defining a target from an origin. And it's important to understand that, the easiest way to understand multi-locations is that they are expressed in relative terms to a given origin. So it's not the same saying that the origin is Moonbeam, that the origin is Polkadot. And you can represent anything. You can represent a chain, an account, a token. And basically the multi-location has two things, and you will see it on screen. It has a parent that defines if we're moving to an upper folder or to a parent folder, or an interior, which can say, okay, in that folder, what are we going to look for, right? So an interior can have here, which you can see here on the screen, which is basically no interior. You can think of it like that. Or you can have, hey, I need 3 fields to define my interior, or I only need 1 field. And these fields have very different determined values, okay? It's not that you can just write text in these fields. So from Polkadot, if we want to target, for example, Bob, which is an account in Polkadot, basically we need 1 field, and we need this field to be account ID 32, which is basically the Polkadot account system. And you can see that parents is 0 because we're not moving to an upper folder. We're already in that upper folder. So if we're targeting a Kala or any given parachain, we would just say parents 0 because we're moving actually downwards, and we can just provide the parachain ID as the X1 value. If we want to target an account inside a Kala, and remember that the origin here is Polkadot, it's not a Kala. So we would actually provide the parachain, we would actually give an interior of X2, we will provide a parachain ID and then an account ID 32 to represent Alice. In the case of Moonbeam, it's very, very similar. The main difference is that for Alice, we need to provide an account ID 20 because Moonbeam uses Ethereum styled accounts. If we want to target a token or a given asset, an XC20, for example, within Moonbeam, we can actually provide an X3 in where we're saying, I want to go to Moonbeam. I want to get to this following palette, which in this case, a palette is like a plugin. I want to go to the XC20 plugin, let's call it like that, and I want to target this XC20 in particular. Okay. It changes a little bit if we're in Moonbeam. It's now the origin is in Moonbeam. If we want to target Aleph or the asset that we talked before, we basically now need only X1 for Aleph or X2 for the asset. because we don't need to specify the parachain ID anymore because we're in that parachain. If we want to target Bob or Polkadot, we just need to basically add parents 1 because we're moving to an upper level now. And if we want to target another parachain or another account in another parachain, it is similar to what we had before, but now we have to specify the multi-location with parents 1 because we're moving from an upper level then down to the parachain itself. So as you can see, it changes only by just defining parents as 1. All right, let's switch gears again and talk about XCM fees. And this is going to be very brief because I want to try to get time to the end for remote EVM calls. But basically, XCM fees, to understand XCM fees, first, I suggest you to visit our documentation site. I feel that I'm just like, marketing our documentation site. But, we do have a lot more detailed information there. But to understand XCM fees, you have to understand what weight is. And weight is a concept in substrate-based chains that is times in picoseconds that an extrinsic takes, or it takes a certain amount of time to execute an extrinsic in a standard hardware, right? So let's say I'm running, the latest i7 and I'm running a balance transfer, and that's going to take, 0.00001 seconds out of my block execution time. So you would transform that time into weight, just saying that, one weight is 1 picosecond. Only for XCM instructions, only for XCM execution, you can actually find a fee coefficient between weight and cost, okay? This is not really valid for regular transactions because regular transactions have things like block capacity and how overloaded the network is and so on. But only for the case of XCM instructions, you can calculate a fee coefficient that in this case, for Polkadot, it's this amount in Planck dots. Planck dots doesn't have decimals, but bear with me. And you can find this amount for Planck KSMs. And Moonbeam in the case of Moonbeam, we use a weight to weigh factor, where weigh is the same as on Ethereum. It's basically the smallest unit that Moonbeam has, or Moonriver, or our testnet Moonbase Alpha. And you can see the factor here, right? So if a call takes 1 billion weight, you just multiply this by this, divided by 10 to 18, then you have the cost in Glimmer. And so basically, the XCM fee can be calculated as a multiplying two things: the weight and the coefficient that I mentioned before. And I brought some examples here on the right-hand side where you have some XCM instructions and their cost in weight. And if you do the multiplication, you should see these values as well. And basically, we provide more examples in our documentation. And at the end of November, I'll be presenting at Sub-Zero. Well, I'll be showing a lot more details about specific examples and so on. All right, let's switch gears again. And before we go to remote EVM calls, I want to give a little bit of an intro to the Moonbeam XCM SDK. The SDK is basically a tool that makes life easier for developers because it abstracts a lot of the complexities. You don't have to understand what units per second is, which is a factor to calculate some of the XCM fees. You don't have to think about weights. Oh, how much weight do I have to provide for the call? A multi-location, what is that? Oh, what is a pallet? It's meant to simplify all those complexities for developers. So a developer building a dApp can focus on build a dApp and use the XCM SDK or the Moonbeam XCM SDK to sort of do all that for him. The SDK has all the asset information like parachain, pallet instance, general key. It has endpoints baked in and some other information that it's basically allows you to deposit tokens to Moonbeam in a very straightforward way. And it's also coded in a way that any parachain can modify the configuration file so that they can add the information of their own pallet, methods, and weight, and so on. So the idea is that the developer doesn't have to worry about that, but other parachain members or Moonbeam can just basically configure set up the configure file. So just to show you a quick example, let's say you want to get started. You basically install the SDK and you can initialize it by just importing the initialized function. And in this case, it's super interesting because you have to provide an Ethereum signer and a Polkadot signer. Because if you're going to move DOT from Polkadot, for example, or let's say A star from A star, you have to sign the transaction using a Polkadot type signer. But if you're going to move the tokens back using Moonbeam to another parachain or chain, you will have to use an Ethereum signer, right? And so that's why you need both. If you initialize Moonbeam, you'll have all the symbols, all the assets, and all the, you can get the information about everything that is supported, basically. And in the case of deposit, it's quite simple. As always, you can find the documentation URL in the top right-hand corner. But basically, you import the asset symbol and the chain key. The asset symbol has all the assets supported, and the chain key has all the chains supported. And you can say, hey, I want to, interact with Dot, and I want to interact with Polkadot. And so basically, you can actually call the deposit function after you initialize Moonbeam, where you say, hey, I want to deposit Dot to Moonbeam. And this provides two methods, a chains and a from. The chains has all the origin chain information. In this case, it would be Polkadot, because it right now it's only configured to be Polkadot. But in the future, we could have, transferring dots from Akala to Moonbeam. And so the other thing is a from function. And the from function, basically, you can use it to say, now, I want to deposit Dot to Moonbeam from Polkadot. It just basically makes sense if you read the sentence like that. And so the from method, you can specify the Moonbeam address that you want to deposit the dots to, and it returns a bunch of things that are helpful to check the transfer logic, to make sure that you can do some checks before ensuring that the transfer is going to succeed, like the minimum balance, the source balance, and so on. And then once everything checks out, you can just basically use a send function to just send a given amount, right? It is that simple. And believe me that if you try this using, Polkadot.js in that palette, it's a lot more complicated. In the case of withdrawals, it's very, very similar. The first part is similar because we're using dots and Polkadot as an example. The main difference is that now, instead of the deposit function, we're going to use the withdraw function. And this gives us a to function. And so now it is, I want to withdraw Dot from Moonbeam to Polkadot. And now we provide the Polkadot address. And in this case, the Ethereum signer, that you don't need to provide it if you already did it when you were initializing the Moonbeam part. So once again, this returns a bunch of information that you can use to check the transfer logic. And if everything is okay, just send the transfer. It is super simple. And so for the SDK roadmap, we want to generalize it to make sure that it's not Moonbeam centric. We want to add also the Transact part. Like I mentioned before, the remote Transact stuff is not added in the SDK. And hopefully in the future, we can also add remote EVM calls through the SDK to simplify a little bit how they're done. All right, XCM, what's to come? And I think I spoiled it already early on, and actually Kevin as well. And so, we're working really hard on how you can access the Moonbeam EVM through basically XCM, so that other parachains can use it and ensure that they can execute smart contracts or Solidity smart contracts through XCM. And so in order to do this, we actually had to code an Ethereum XCM palette. So it's similar to the Ethereum palette, but it's different because we're going to see how the flow of an Ethereum XCM transaction is, and you will see some differences there. But basically, this palette is a middleware between the Transact XCM instruction and the Ethereum palette that you already interact with when you do a call to the EVM. Another key element of the remote EVM calls is something that I mentioned before. It's the keyless accounts that are controlled by another account from an external chain through XCM. And this is obtained when the instruction has a descent origin in it, like we saw before. Or you can actually do you can define the message sender of the remote EVM call using a proxy or a proxied execution, basically, right? So if I have my multi-location derivative account, and you can find a lot more information about how this is calculated in the doc side. But you can say, okay, I want create a proxy to that multi-location derivative account so that it would still pay for the fees, but the message sender, which is a very important thing in Solidity contracts or in Ethereum contracts, you can actually own the private keys of that message sender. So let's compare a regular and remote EVM calls, and this is going to be the happy path. We don't want anything failing here, so we're just going to show you the happy path. So we have a user that it's happy because it's interacting with Moonbeam, and this user, wants to transact with a given smart contract, and this is all inside Moonbeam. And so the user will just submit a signed transaction, and this is in Ethereum style signature. And so basically this will get picked up by the Frontier RPC extension, and Frontier RPC extension will work together with Pallet Ethereum sort of to validate the transaction, make sure everything checks out, and it's going to send the validated transaction through the EVM pallet to the Rust EVM. This is super simplified, but it's just to show you the main point, right? So, once the Rust EVM executes everything, you have some execution results, and then you have some Ethereum logs that you can see on Moonscan, the Etherscan Moonbeam Explorer, and everything is cool. The user is happy. Everyone is happy. So what happens when you do a remote EVM call through XCM? It is a little bit different because we have now a different chain, right? And that chain can use substrate style or Polkadot style signatures like SR25519, or it can be another, chain like Moonbeam that uses Ethereum style accounts. But the important thing is that this user is also happy because, they're using Polkadot. And so, they submit a signed XCM transaction. But that XCM transaction has a Moonbeam EVM call inside of it, okay? And then this through the XCM, we're going to use the XCM transact instruction, and that's going to change the origin. Remember that I said that, the origin will change with the descent origin instruction. And so the Pallet ETH Ethereum XCM is going to do some checks to ensure that everything checks out. But you're going to see some differences. And that's why, we cannot use Pallet Ethereum to check some stuff. And you're going to see it in the transaction receipt that I'm going to show you. And what's going to happen is that, the Pallet Ethereum XCM is going to send the validated transaction through the Pallet EVM to the Rust EVM, and then everything else is going to be the same. The main difference here is that the user on the origin chain will be signing the transaction, but the dispatch will be from a different account, this keyless account that I've mentioned before. And so basically the transaction that the Pallet Ethereum XCM constructs, it's not signed. It doesn't have a signature, basically because it's trusting that the origin controls the private key, basically, right? And so there's some differences. As you would have noticed from the diagram before, there's some differences between one and the other. One of them is that remote EVM calls have a global nonce, right? So because this is to avoid EVM transaction hash collisions. The second one is because there's no signatures, you cannot do easy recover, right? You cannot recover the sender from the signature. However, the sender, the from, is still included in the transaction receipt and in the transaction by hash methods. And that the gas price is 0 because the call is charged at an XCM level, not at an EVM level. So if we get a transaction by hash of this hash that it's a remote EVM call from the Ethereum JSON RPC, you will see this is a response. And if you check the signature values, which are the VRS, they're all 0x1. So you cannot recover the sender from the signature. However, you can see that the from is there. This is the correct sender. And then another important thing is that the gas price is set to 0 because the execution is charged at an EVM level. Okay. So I do have 8 minutes, so I'm really happy because I can do a very, very quick demo about how you can construct a remote EVM call. And I have some information here. I have the URL of the docs in case you want to do this, in another time. But basically, we're going to need units, which is a relay chain token. You're going to have to calculate the multi-location derivative account. In this case, it's this one, the one that I'm going to use, or the one that is going to execute the call. And we're going to interact with this contract that I have shared the URL. And we're going to use this method. This is the selector of the method, which is just a simple incrementer. It's going to increment the value by 1. This is an encoded call data because we're going to go through it a little bit quicker. And then we have important links down here in case you want to sort of like check this out some other time. So I'm going to skip out of the presentation mode. And the first thing that I'm going to do, I have the relay chain here. This is where I'm going to, initiate the call, the remote EVM call. This is Moonbase Alpha. And then I have the incrementer contract here. And we can see that the number of the contract is basically 2. We also store the sender and the timestamp just that you can verify that, we're going to increment it by 1. And this all checks out. So the first thing that I have to do is go to Moonbase Alpha, and we're going to build our encoded call data. All right. So this is the bytes that are going to be executed on Moonbase Alpha through the Transact XCM instruction. Okay. And so basically we need to select the pallet, which is Ethereum XCM, the Transact method in this particular case. we're going to use V2, which is the latest version of this let's say primitive or the XCM transaction. And this is all you have to provide. It's very, very simple. You just need to provide a gas limit, the contract that you want to interact with. We are not sending any def tokens or any glimmers or any movers, so the value is 0. This is the same as the message value in the Ethereum transaction. And this is the input, which is also referred to as the data. And this is basically, in our case, this is the selector of the function that we want to interact with, right? If you want to know how to calculate the selector, is basically by calculating the catch_256 hash of the function name. And if it would have any inputs like an address or a number, you would have to put the types here. And you just grab the first 8 hexadecimal characters, and this is the function selector, okay? So the next thing is to copy this encoded call data and then go to the relay chain or the origin chain, and then you're going to build your own XCM message. Because we're a little bit short on time and I want to make sure that we are on time, I'm just going to go ahead and copy the encoded call data. And I'm going to show you quickly what this XCM message looks like, okay? Basically, we're going to use Alice from Polkadot, or the relay chain in this case. We're going to use the XCM palette, and then we're going to build our XCM message. The destination will be parachain 1000, which is Moonbase Alpha. And then we're going to build our XCM message, in this case V2, the version 2 of the tech, let's say, of the message, the version message. And then we're going to add the instructions. In this case, this palette in particular basically includes the descent origin instruction and injects Alice's address. This is to ensure that no one can impersonate no one else, right? Only the owner of the private keys of Alice will be injected into this descent origin instruction. So now we only have to include 3 instructions, which is withdraw assets, in which we provide the asset that we want to withdraw. This is, in this case, dev tokens, and we're withdrawing a specific amount. We're buying some execution time. And in this case, I'm just saying, hey, I want to buy 0.0001 def of execution time. I don't really care about the weight that this accounts for, but this is enough. And you have different ways of configuring this. And the last instruction is a transact. We need to put the origin type as sovereign account. And I'm not going to explain this why, but this is in our documentation site. There are different origin kinds basically in XCM. We need to say the amount of weight. So I consider that 7 billion weight units, or 0.0007 seconds of execution time, is enough. There's some math you can do around here to get a more robust estimate, but I'm overestimating in this case. And last but not least, we have the call that we want to execute. And in this case, it's basically what we want to execute is this bytes that we got on Moonbase Alpha. Okay. So what I'm going to do now is that I'm going to submit my transaction. Hopefully this works because this is a live demo. So I'm going to sign it, as you can see. And then we have, we're waiting for our relay chain to transmit this message, to broadcast it to Moonbase Alpha. And then that's it. We're going to go to Moonbase Alpha and make sure that we receive the message, right? So in the next block, hopefully the gods of live demos are merciful with me. So we have here the downward message. So DMP, like I said, was processed. And we can see that, the Ethereum transaction was executed from this account, which is the account that I showed you before in the slides. This is a smart contract, and this is a transaction hash. And everything seemed to have basically worked correctly. So if I go to, the incrementer contract and I reset it, remember that this is 2. So if I reset it, it should be 3. And if you check the timestamp, I don't speak Unix timestamp, but this should check out with more or less the last block. So yeah, I mean, sorry that I had to rush through it. There was a lot of info that I wanted to cover, but I'm happy that I was able to at least show you the demo. I left in the Google slide, and sorry, in the slides, I left all the information. If you want to do this yourself, we're happy to help you out in Discord and Telegram if you need help or you want to try this out. We do have some parachain teams already, using this on testnet, which is super exciting and super encouraging to see. Don't think that I thought about sharing the presentation with you. You can scan this QR code or simply visit Moonbeam XCM Illuminate 22. So If I'm going to try to copy this, and I'm going to have Kathy or someone share it in the chat. So if you want to get in contact with us, Moonbeam.network, our documentation side has a lot of great material, Telegram, Discord, Twitter, all the good stuff. Thanks a lot for tuning in for Illuminate 2022. Super excited to be part of this. And yeah, I'll see you the next time. So thank you.
That was amazing, Alberto. I'm thrilled you had time for the demo.
Yeah, definitely. It was tight, but I made it. So yeah, thanks a lot, Kevin. Great job. And yeah, I'll see you around, everyone. Cheers.